Oh, all right. So we'll be doing now introduction to atomic theory, that is organic chemistry. So this is lecture one of your lecturers. Okay, they normally use this format: introduction to atomic. Now just pay attention, listen to what happens with these atoms. That's when you understand that organic chemistry itself. All right. So without wasting our time, shall we start? So CH260 is actually a very simple topic, provided you understand some basic stuff. If you understand, you'll be really a scientist. Okay. So the first thing that we are talking about now is an atom is a fundamental piece of matter. All right. So matter is made up of an atom. Okay. So this matter that I mean, matter is anything that we see around us, okay? So that thing we see around us, it can be a table, it can be a chair, it can be your PC. It's made up of very small things called matter, all right? Matter is anything that can be touched physically. So anything that we can touch is actually matter, all right? So whatever things you can touch, your clothes, if stuff like that, your food, stuff like that, your drink, your what, that's matter. It's made up of very small particles. So everything in the universe except energy. Energy, because you can't touch energy. That's why we say anything that can be touched is made up of matter. I mean atom. So everything in the universe is made up of atom. That's all. So everything, I said everything in the universe is made up of atom. So this type of atom can be different depending with the substance we are dealing with. Okay. All right. So an atom itself, it's made up of three. An atom, by the way, it's a particle. All right. So the same particle now, it will be made up of subparticles called protons, neutrons, and electrons. Okay. The structure will look like this, where we'll find the protons and neutrons inside, which are making a, what we call a nucleus. Then outside there, we know that we find electrons in the shells. Okay, so these are the electrons, and we'll be doing more of these than any of these two. Okay, so that's the structure of an atom. It is made up of three subparticles, which are protons, neutrons, and the electrons. Okay, so these electrons now, like we said, now they will be in charge of every bond that will be forming. Okay, so now, the negative electrons are attracted to the positive nucleus by the same electrical force which cause magnetic to work. That's what keeps electrons together. I mean, atoms together. So, for example, what I'm trying to say is, okay, what I'm trying to say is an atom will be there, right? There's protons and neutrons inside the nucleus there. There are electrons there. So what will happen is that these electrons are kept together. They can't leave this. Why? Because there's a force that is felt from inside there, from the nucleus, and we call it effective nuclear charge. So it's a charge experienced by these electrons. All right. So it is the charge experienced by these electrons. Okay. Let me demonstrate it properly. So what you are trying to say is electrons will be kept in the nucleus. They won't fall. There's a nucleus there which is made of protons, I mean positively, or to say positively. Then there's a negative, the negative electrons here. So there's what you call effective nuclear charge. Is a charge experienced by valence electrons. These electrons that are in the outermost shell, they are called valence electrons. So actually this attraction between them, because here they are negative, here it's positive, so there's attraction. So that attraction keeps these electrons in these shells. That's the reason why, unless a specified amount of energy is actually given to an electron in a specified shell, so that it can jump to another shell. Okay, so we need that. So the negative electrons are attracted to the positive nucleus. So overall, the nucleus is positive by the same electrical force which cause actually magnetic to work. So when you bring magnet negative, I mean north and north, they will do what? They will repel. So, but when it is south and north, you find that the magnet will attract. Why? Because of opposite charges. Okay. So now from there, That's about an atom generally, okay? Okay, so these electrons now, electrons and orbital. Remember, we said just electrons, they are found in these shells, right? Inside the shell there is also what we call orbitals. There are different types of orbitals, but we'll mention them. There are four of them in our studies, or just the main orbitals. There are four. So these electrons actually, they are found, this is the shell, all right, the energy level. So this energy level now, electrons will be found there, but there's a specific part there inside, and we call them orbitals. So an orbital, it's actually just the maximum space, or a space in an atom where the probability of finding an electron is maximum, not that it's found there, it's just maximum, okay? Yes, why is it maximum? Because you can find it in SPD orbital, but what we know is that it is found there and it's maximum, okay? All right. So what we are trying to say is, uh, so that means chemistry is all about electrons, okay? Because now electrons will be now our fundamental study in this organic chemistry. So without electrons, we are doomed. So electrons actually is actually um the chemistry that we'll be having now in this organic chemistry. So a shell is a pathway followed by electrons on an atom. So what we are trying to say is you find a shell there. So this shell, that's where now we find the path taken by what? Electrons. Electrons will be rotating like this, okay, trying to stabilize their actual environment. So we'll find electrons there, okay. So subshells, a subshell will be an area in which an atom moves within the shell. We call it subshell, all right? Then they are made up of SPD orbitals. So these are the shells now that, I mean, the subshells that we'll be finding, okay? These are the subshells that we'll be finding, okay? That's all. So just a moment. Okay, ndabona ndichitabo heyi ndituma kwa computer ndibola. All right, so I'm sorry, I was just someone called. All right, so we are saying now a subshell is an area in which an electron moves within the shell. So within the shell, we find again some subshells called orbitals. That's why I was saying we find it different. We can say it's a maximum. The probability is maximum of finding an electron in the orbitals. Why? We can have S, P, D, F orbitals, even G. We can go to that extent, okay? So just get to say electrons now will be our mother of chemistry, all right? All right. So these now electrons, okay, so like we have now subshells which are orbitals, all right? So we have just a shell which will represent energy level, then, or principal quantum number if you are to relate that. Then subshells will represent now these what we call orbitals, all right? So we have SPD orbitals. So the number of orbitals, um, so AC orbital looks like this, all right? So only two electrons can be there. So I mean the orbital itself is the box, okay? So if I'm to talk about p orbital look like this. So there are three boxes. That's why we are writing three there. Then d orbitals, there are five boxes, okay? So the maximum of electrons, the number of electrons that can be found there is 10 when you pair them like that inside, okay? Okay. So that's what we mean when say the number of orbitals. Orbitals are those just a square box like that. Okay. So S orbital S subshell, it has how many orbitals? It has 1. Okay. Then F, it has 7, which can accommodate maximum of 14 electrons. So these are the electrons that can be accommodated. All right. So that is it. So now if we are to talk about now these shells, okay, I'll repeat. A shell is a pathway followed by an electrons around an atom. So a shell is just a pathway, all right, but inside the shell we'll find something there. So now a subshell comes in to say it's a path in which an electrons move within the cell. Okay, so this was just around the atom, around just the atom of nucleus. Okay, but now a subshell is now talking about within, so we are more of specific now. Then an orbital is a mathematical function that describe the, in short, you can describe an orbital as the maximum area, okay, 3D area, where the maximum like the probability of finding an electron is maximum in these orbitals, because it will be there to be more of specific now to trace an electrons. It's more like you are in the house. That's now in the house, it's the n value, which is the principal quantum number. Then we say we are in the house, in the room, that is now the orbital. You get, I mean the subshell. Okay, from there then we specify more. Okay, like we are just giving an electron address if we are talking about quantum numbers. The name of quantum numbers, we said a shell is given a principal quantum numbers, a subshell is given angular momentum quantum number, then an orbital is given magnetic quantum number. So what I'm trying to say is here we give the value of n. Let's say the shell is equals to 1. Then here we are giving now the angular momentum number. For example, ml, which is the angular momentum number. Okay, it can be 0, that is for s orbital. It can be 1, that is for p orbital. It can be 2, which is for d orbital. It can be 3, which is for f orbital. Okay, that's the value of L. So now we are trying now to be more of specific. An orbital is given a magnetic quantum number. Okay, so here an orbital will get, let's say, the magnetic quantum number that we have. Let's say it's or s orbital, it will have these values. Okay, I mean p orbital, whereby it has how many? 3. So we have 1, 0, -1, like that. These are the values that can be. We are trying to trace electron address where it is found. That's the reason of this quantum number. Otherwise there's nothing like that. We rent this. What is important now is this part: an electron configuration of carbon. We can do a lot. So this is how we write electron configuration. Please pay attention in case you forgot from NS. Okay, in case you forgot from NS, what we are trying to say is this is how we write electron configuration. When you look at carbon, carbon has how many? 6 electrons. Okay, the proton number is 6. So what you do is you write S, P, D, F. Okay, so now you repeat this going this side twice, again you come there twice, again you come there twice, again you come there twice. Okay, that's how we write it of any element. So I will say S, I'll repeat twice, then I'll come now at P to S twice. So we say P, S, P, S. You do the same until you reach F. But for this, I know for carbon now to be scattered. Anyway, let me continue with the trick. SS, we have gone this side. Then PS, we have gone this side. Then D, I'll say D, P, S, D, P, S. You see, I can write again FDPS, FDPS, then I'm done. But for these electrons that will be given in your test, they are enough. So you start numbering S, you number them to say 1, 2, 3, 4. That's how they will be starting with their initial values. So P to start at 2, then D to start at 3, then F it will start at 4 if you are to continue for F. Okay, so that means for S you start 1, you have already counted there, then you have 3 there, you have 4 there, you have 5 there. Okay, then you have 6 there, then you have 7 there, then you continue like that. But what I'm going to choose is, I know S orbital can have 2 electrons, 2 electrons, this one 6. You see, I'll just write how many here? 2, so that because I'm lighting for carbon. Let me lab with this. I was just showing you. If you can't get this trick, inbox me. I think the line I've shared the line there. Mm, mm. So you can inbox the line is 0964 122 411. So I can share the video on that. I won't attach to this one, but I can share to you. So we had 6 electrons, so here will remain with 2, right? So this is the electron configuration, but the noble gas electron configuration will replace the lowest or the maximum number of group 8 that we can use and replace there. That's why we have replaced there. For helium, we have 2 there. So this one was substituted by helium because that's the configuration of helium. Okay, you replace the configuration of those group 8 that can be accommodated in that configuration that you have put. So you should be familiar with how to write electron configuration, please. For example, so valence is the measure of potential of the atom of an element to form a bond. So that's valence is just the potential. Then there's valence E, which are just electrons in the outermost shell. Okay, so you should differentiate the two. Okay, so I can pick any element that I want to write the electron configuration. Suppose for oxygen, which is 8 protons, so I'll say S, I repeat, then P, S, P, S. This is enough for 8 electrons. So I'll say 2 there, 2 there, 6 there. No, this they are making 10. So I'll have 4 there. All right. So I'll have 4 there. So I'll say 4 there. Okay, that's for oxygen, eh? Then that means I end there. So I can now I can now put 2 there. I'm counting the S's that I have. Then we said PO start at 2. All right. So this is the electron configuration for oxygen. So be familiar with how to write electron configuration, please. I have the video for on electron configuration. You can just watch. Thank you very much. Otherwise, this is actually what we had, and you can try in. Okay, like phosphorus that's 2, 4. That is 10, 12, 15. Okay, so it has 15. So you say 1 S S P S P S. Okay, I think these are enough. These are enough. So we say 2 electrons there, 2 there, 6 there, making 10. Okay, then again there we are making 12. 12 we are making now. Okay, 12 we need 3 now to add there for to make 15. Okay, so meaning this one is not counted. So we start numbering S 2 3. Always P start at 2, like I said, then this is 3. So this is what you can see there. All right, so thank you very much. Otherwise, that's for electron configuration. This is it, part 1. Watch out for part 2. All right, thank you very much. That's atomic now. Okay, so this covers industrial chemistry, pure chemistry, education chemistry, and also other type of chemistry, organ chemistry. Okay, CH260. Thank you very much.